Hello everyone, thank you for joining me again today. We've got a repair which I'm going to be showing you on a Marconi microwave radio test set. This particular radio test set is one I have, which is a microwave test set, what's called an MTS. I did another video earlier on, a couple of months ago, regarding the microwave test sets and what they're used in and the applications that they're mainly used for. This particular test set goes from 10 MHz to 20 GHz. It's a model 6200A, and then you can get the add-on bit at the bottom, which is the reflection analyzer, which gives you a lot more features such as polar diagrams, the Smith chart, impedance, all kinds of reflection characteristics which you can test, S parameters, all sorts of advanced features which you can use the reflection analyzer at the bottom. The reflection analyzer at the bottom goes up to 26.5 GHz. You can get different models of these Marconi test sets. You can get the different models that go up to size 46 GHz. Some go to 2 GHz. There's sort of 3 or 4 models in the range. I've got another one here, which is again the same model, which is a 6200A microwave radio test set. This one has a fault on it where the vernier control for the RF output level doesn't work. Doesn't matter what level shown on the screen and what you set on the output power or the signal output from the signal generator output, it doesn't give the correct level. And basically what you do with these radio test sets when you calibrate them is that there's an instrument menu through the utilities feature, and you can select instrument calibrations, and what you do is you calibrate first of all the power sensor that's plugged into port D on the reference port, so that's calibrated correctly, zeroed, then calibrated first before you do anything, and then you connect it like this to the signal generator output. And then you go to the instrument calibrations menu, which is password locked by Marconi, but I have the password to enter that menu. And once you're in that menu, you can select broadband or narrowband power measurements, and I'm going to show that in the next video that I'm going to do. This will be part 1. And you can select, say, in narrowband mode, any frequency from 10 GHz to 20 GHz. It'll calibrate that, the instrument, across its entire frequency range. Now, on these power sensors, there is calibration data that you have to enter into the test set before you do that, which is contained on the side of the sensors here. There's things like calibration factor, linearity factor, and the data on the different frequencies right the way from 0 to 20 GHz, which you have to enter in order for the test set to be aligned with the sensor and obviously to calibrate it correctly. Now, this particular radio tester here that I've got open to show you, which is the same model as that one there, this one just gives a high output level. Normally in radio test sets, if the RF output level isn't there, it's normally the amplifier stages or an open RF path. But the output on this varies depending on what frequency we select. Now, there's not a lot in these test sets, to be quite honest with you, for the price that they obviously retailed at, in comparison to the Marconi 2955, 2945 models and the 2968 and 65 radio comms test sets are cram-packed from bottom to top with boards and RF screening cans and RF sub-assemblies and all sorts of goodies. In the microwave test set, it's actually quite sparse inside, and I'll give you a bit of a demonstration of its internals. This particular test set has the option for the step attenuator, which is here. That's what this module is. That's the step attenuator. That's not fitted on all radio test sets, these microwave test sets. But what we've got on this particular test set is with no control of the RF level apart from what the step attenuator does. And there's actually which is difficult to see from here, but I'll explain first. The signal sources are actually derived from yigs, yig oscillators, which are these three. And obviously on the higher frequency models, the 46 GHz version, there's a fourth yig that goes here. These are the mounting holes for it. So basically you've got a yig that starts at the very low frequency from 2 GHz up to, I think it's 8 GHz, then from 8 GHz up to, I think it's something like 12 GHz, and then from 12 to 20 GHz. So that's why you've got the three yigs. They're going to directional couplers, which you can see just here. There's 1, 2 there, and that one connects straight into this pin diode switch mechanism here. And then from there it goes up into an isolator, and it works its way eventually to the step attenuator. But just prior to the step attenuator, there's actually a device which is something I'm going to try and focus on. Let's have a look. I think I've got the zoom a bit too much. Let's just try and reduce that a bit. There is a pulse modulator, which is this bit here, which then can modulate the carrier. And if I just turn the test set round, I think that would be the best thing, because obviously it's quite difficult on the bench with the way that it's orientated. What we've got is, again, this is a top section of a step attenuator, this is the other side of it. But right down there, and I think it's just almost impossible to see, but there's a pin diode attenuator which is just here, and the output of the combined signals from the yigs, basically from 2 GHz to 20 GHz, well 10 MHz to 20 GHz, is fed in here, and this pin diode attenuator then output goes to this step attenuator. And what the pin diode attenuator does, it's got a piece of coax to it which provides a voltage, and it's a control voltage which controls the amount of RF attenuation that's allowed to pass through. So the RF signal coming here is allowed to then pass through the attenuator to this step attenuator. On models where there isn't a step attenuator, this output coax goes directly to the N-type connector. So this pin diode attenuator here isn't adjusting. Now there's a DAC value inside the calibrations menu within the test set, which sets the voltage that's given over the entire frequency range. So we've got a 10 to 20 GHz frequency range, and as per the calibration of the power sensors that I spoke about earlier, that'll self-calibrate, and the microprocessor will then adjust the DC voltage levels to the pin diode attenuator here to match the level that it should be giving out in power. So it reads its own power level and then stores that in memory and calibrates it across the entire frequency range. Now it's failing that calibration sequence on this particular test set. And so what I've done, I've measured the voltage there on that piece of coax, which is one of these coaxial connectors, where we've got a piece of you know, it's like signal coax, this white coax stuff here, and it suddenly jumps from, because normally I would have expected the pin diode attenuator to be stuffed, because sometimes people transmit high amounts of RF power back into the test set, which these are not designed to do, by the way. They're not like the other radio test sets where they can take hundreds of watts of RF power, or 70 watts or whatever rated that they are. These can only take milliwatts reflected power back, really. Otherwise the attenuator burn out, or the pin diode switch burns out, and that's what I initially thought might have happened here. But testing the control voltage to the, or looking at the control voltage to the pin diode attenuator module, you can quite easily see that the voltage isn't being manipulated. It's not moving much. It gets to a certain point with the DAC value in the calibrations menu, where it counts from 0 to 655,000 or something. you get to a certain value and suddenly it switches from giving high output RF level to next to nothing on one DAC alone, whereas obviously each minute change in the DAC would manipulate the voltage just ever so slightly on that pin diode attenuator and adjust within half a dB, 1 dB steps on the output, the RF level, and that's not what's happening here. So I don't suspect that it's the actual pin diode attenuator. If I just try and zoom in down there, it's right down there, it's very difficult to get to, and indeed just to get to this level of repair you've got to really strip the test set down. And so basically there's a synthesizer block which is here, a big heavy block, and this controls the pin diode when it focuses. So this controls the pin diode block. There's a connector on the top just there, which is difficult to see. This is where all the pin diode switches and the Yigs connector, they all plug in there. And then on the other side we've got basically a really heavy block, must weigh about 10 kilos that. And what I found is that there's a transistor on this board, which in conjunction with a resistor pack and a chip, a 748C series chip, controls the voltage. Now, one of the things that you'll find when you're working on these test sets is there's no circuit diagram. The service manual just gives you a block diagram, and I've not been able to successfully find a proper schematic diagram for these test sets, which is very, very unfortunate. But I've been on forums where people have said that they do exist, these diagrams, but I haven't been able to manage to get one yet, so still up in the air. But the digital board, which I shall get and show you, this is that's a time-based PCB which goes in the on the analog synthesizer board. The synthesizer board, just to explain, this module here controls frequencies from 10 megahertz to 2 gigahertz, and then from 2 gigahertz upwards is controlled via the Yigs, which are mounted on here, the Watkins and Johnson's Yigs that are there. So this takes care of frequencies from 10 megs to 2 gigahertz synthesize. It's also the frequency counter section, and then the Yigs then produce the higher frequencies, and that's how this works. This is a digital board, and this is a sort of logic that's on it. There's plenty on there, but the issue with this, and obviously it's something that I'm going to have to look at. There seems to be, not sure where it is now. Oh, it's on the other side, of course. There seems to be on here a bit of resoldering work that's been done in the past on the connector, and some of these joints on this connector that plugs into the synthesizer board and also to other boards appears to look like the dry joints to me, or they've not been soldered very well. So I'm going to redo all these. There's some pretty bad soldering on some of these connectors, so it could be something like that, you know, that the connector itself's causing the problem instead of the board. I mean, if push comes to shove, one of the 748C chips that's on here, plus one of the control transistors that I found, could be changed, but I don't think it is that kind of fault. I've got that feeling. I don't think it's a failed IC or a transistor. I could be wrong, you know. I'm going to have to try and do some more fault finding. But in order to get to this level, you've got to strip it all out, and it's very difficult. There's a lot of rigid coax that I haven't shown you yet that's had to come out, boards and other things that are all in here, mounting brackets, because it's all fairly crammed in. And yet what I don't understand is this section here, this is a power supply at the back, all the way up here is all big empty space, and I've no idea why that is, because you don't find that in other test sets, I can assure you. Every centimetre is full in a radio test set, but for some reason in these there are not much gubbins in it on the RF side, so much as, you know, the logic board just sits here in this section, which I'll show you in the next video when I do a calibration routine on this test set when I've got it all back together. But the first thing I'm going to do is I'm going to resolder the logic board connections to this synthesizer module, and then I'm going to put it all back together, and then I'll show you the next video, which will be the calibration routine and how to do that. So thank you very much for watching, and I will be to you in the next video. Thank you.